where we're going to perform a simple linear regression. So let's say given the class data set, so it's class.csv, with 5 variables. We have name, sex, age, height, and weight, representing the information for a class of students. Predict the weight based on height. So first thing we need to do is set the working directory wherever your CSV file is saved. You want to use C. We use forward slashes in R, and mine's saved at C users mat desktop. Control Enter will run that command prompt. We can use get working directory to verify, and that's where it's set. So now let's call our dataset class and import the CSV file using read.csv command, and the file name is class.csv. Now we read that. Over here we have data class 19 observations with 5 variables. Well, considering we said we have 5 variables, that's a good sign, but let's make sure. So we want to view class, and it looks like here we have name, sex, age, height, and weight. Perfect. 19 rows. Okay. So what do we want to do before we build this model? Well, we want to explore that data to make sure it's relatively accurate. Oftentimes we'll never know completely if it's 100% accurate, but by exploring the data we can get an estimate of that. And another thing you'll likely want to do is visualize the data. Now, while we won't do that in this demo, it is important to visualize the data to tend to see if a relationship does exist. So what do we want to do? Well, first we want to look at the structure of the data to make sure the data ingested was appropriate. So we have name as a factor, and it could be factor or character string, but factor is perfect. Sex is a factor with 2 levels, F for female, M for male, and you see they get re-encoded as 2 or 1. We have an age as an integer, and then we have height and weight as numeric. A command you'll probably want to use as well is summary. So what summary will do is it will look at summary statistics of our data. So with these factor variables, you can see it shows the first few names and the count of that. Obviously it's 1 because each person has an independent name and there's no repetition. For the sex factor, we see that there are 9 females and 10 males. And then for our numeric variables, age, height, and weight, we get the minimum and the maximum. We get the first quartile and the third quartile, which will allow us to compute the interquartile range and create box and whisker plots. And then we have the median and the mean. So the age range here is 11 to 16. Might be a wide range for a class, but at least somebody in here isn't 90 years old or 0. The height is 51 to 72. That sounds appropriate. There are no negative values. And weight is 50 to 150. So if we want to build a linear model now to predict weight based on height, we're going to use a function called LM. So let's label our model results, and we use the LM function, and we say the formula that we're trying to compute is weight on height. So we're trying to predict weight, the y variable, based on the individual's height. And the data is from that data set called class. And so we run that, and let's print the results. So we see on that linear model that the y-intercept is negative 143.027 and height is 3.899. So in a model, we have y, which is weight, equals negative 143.027 plus the individual's height times 3.899. Now, there's a couple other things we can do. First off, you can also run the linear model, again with the formula command, but instead of saying that data equals class, we could just use the data set and the variable name and predicting class of weight times class height. And now we don't have to specify data. If we run that, and then we print the results of results 1, we see the numbers are exactly the same. So you can use either of these for your modeling process. Now lastly, we want to test and understand the accuracy of the model. So what we'll do is we'll run the summary command on results. So we're running the summary on the model itself. When we run that, you can see here that the residuals based on the min, first quartile, median, third quartile, and max range. That is ultimately less important because you need the sum of squared residuals for meaningful insight. We have the coefficients. So again, here we have that negative 143.0269, and height, we have 3.899. We also have standard error and t-value, which are a bit less pertinent, but what you really want to look for is this probability, this p-value, and these significance codes. So what you're seeing is the intercept is significant at 0.001 accuracy. So we're 99.9% confident of the accuracy that the intercept is significant to the model. And technically, you don't have to worry about the intercept being significant or not significant. It just needs to be included in the model. But we do need to know if the predictor, height, is significant to the model. And so we have 7.89 times e to the negative 7th power, so that's 7 decimal places, so it's 0.000, etc., 789, which provides a p-value score that is significant at 0.001. So we have our overall residual standard error of 11.23 with 17 degrees of freedom for the model. We have our multiple r squared of 0.7705 and our adjusted r squared of 0.757. Now remember that adjusted r squared is being used to compute based on the sample size and the number of variables in the model. So you want to use that adjusted r squared and not the multiple r squared in regards to scoring your model. So this shows that we're 75.7% confident in the results of this model for height being able to predict weight. And again, here at the very bottom, you have the overall p-value of the model. Because there's only one variable included, the p-value is equal to that 7.887 or 7.89 reduced. And you also have the f statistic, which is sometimes used.